In this video, we are going to discuss about two single-phase clock register, TSPCR. So earlier we have used two-phase clocking scheme. So in the two-phase clocking scheme, that is clock and clock bar, the care must be taken while routing this two. And we have to ensure that the overlap between the clocks should be minimized. So if you see the C square mass register, it is tolerant to the clock skew, but we can able to design the register based on the use of single phase clock. So this this TSPCR is proposed by Yuan and Svensson, who uses a single clock. So first let us discuss about the positive latches and negative latch. Okay, so this is nothing but a positive latch. So if this is a clock, okay, if this is a clock, this part is called as a positive latch. That is whenever the input during this time, if the input of let us see, so if this is ln means during this time only the ln value, that is the input value, will reflect in the output. Okay, so if you see, this will be 1, okay, and it will be 1 for till this negative phase, and it will be 0. It will be going to 0 during this time. Okay, so this is my output. So let us see the working. Okay, so whenever the clock is 1, the clock is 1 means this PMOS will conduct. Okay, these two PMOS will conduct during the. So this becomes one inverter. This is an inverter, and this is also inverter. The inverter is called as NOT gate. Okay, so you have two inverters. Okay, so the input, if the input value is 1 means this becomes 0, then my output goes to 1. So the input will be reflected at the output. So if it is 0 means this becomes 1 and this becomes 0. Okay, so what happens when the clock value is 0? So if the clock value is 0 means this will be open circuited. Okay, so this will be open circuited. So if I give the if I give the input value is 1, so if I give the input value is 1 means this transistor will conduct. Okay, but this X becomes floating. Okay, so the input will not go to the output. Okay, so the output will be in floating. So output goes to high impedance state. Okay, that is hold mode. Yeah, and the hold mode. So if the input value is 0, the PMOS will conduct. So the X becomes 1. Okay. Maybe as this is not over. So the output is taken from scale. So this is my circuit. So if the x is 1 means here also the output is floating. Okay. So the output is in the hold mode. So this is my circuit. Okay. So you have to take the output from above the NMOS. Okay. So this is about the positive latch. So whenever the clock value is positive, the input will be reflected at the output. So it is called as transparent mode. And whenever the clock value is 0 means the output goes to floating. Okay. So let us discuss about the negative latch. Okay. Right. So this is my negative cycle. So this is my clock. Consider my input as so this is my input. Okay. So the output will be, so this is my negative clock. So it will be 1 for the whole period. Okay. After that, it goes to 0 to 1. Okay. Then it will be like this. Then during the negative half cycle, it will be like this. So okay, this is my output. Okay. So whenever the clock is 0, if the clock is 0 means, so it will be short circuited. Okay. So if it is short circuited means it will look like this. So it will be looking like the two inverters. So it is same as that one. Okay. So it is in the transparent mode. Okay. So if the clock is 1, so whenever the clock is 1, it will be open circuited. So if input value is 0, if input value is 0 means this PMOS will conduct, so it will not reach here. So my output goes to high impedance state. So if the input value is 1, this NMOS will conduct. So this X value goes to 0. So if X value goes to 0, this PMOS will conduct. So again my output is in hold mode. So with the help of this TSPC, I have an additional advantage that there is a possibility of embedding logic functionality into the latches. So I can implement any logic like logic gates. I'm going to implement the OR gate using the TSPC positive latch. So I'm going to use a positive latch. So you can see, so here I have a pull-up network and this is a pull-down network and I have a clock. So this is also inverter. Okay. Inverter, I have a clock here. Okay. So to implement OR gate, so here I have constructed the NOR gate. Okay. So if I want to construct NOR gate, A plus B means it has to be connected in parallel. So if NMOS is connected in parallel means PMOS should be in series. Okay. So this is my A bar and this is the inverter. Whenever the clock is 1, if clock is 1, this will be conducting. Okay. So this will be conducting. So the circuit will look like this. Okay. So my Q is nothing but A plus B. Okay. So if clock is equal to 0, the output is floating. So it is nothing but a positive latch. So next I'm going to implement the negative edge trigger register. So this is nothing but the positive latch, okay, which we have already seen, and this one is nothing but a negative latch, okay. So if I combine this one, okay, so this is a positive latch and this is a negative latch, okay. This is a positive latch and sorry. This is a positive latch and this one is a negative latch. So during this time, okay, during the negative edge of the clock, this is called as negative edge trigger register, okay. So during this time, the input will reach the output, okay. That is why it is called as a negative edge trigger register. So it can be constructed by cascading the positive latch with the negative latch. So what is the advantage of using this one is it uses a single clock phase, okay. But it has a disadvantage that the clock load is similar to that of the conventional transmission gate register or C-square MOS registers. So you can see how many transistors are there, 3, 6, 9, 12. So there is a slight increase in the number of transistors, that is 12, okay. So if you see, if that there is one more problem. If the clock value is 0, so if the clock value is 0, this output is floating, right? This is the output node is floating, therefore it is exposed to the coupling from the other signal. So it also has a charge sharing can occur. So if the output node drives the transmission gate, so therefore this floating node should be isolated with the help of the static inverters or pseudo-static for improved noise immunity. So this TSPC latch circuit can be reduced further here where only the first inverter is controlled by the clock. So if you see in the positive latch, I have used the clock for 2 transistors. So now I am going to use only 1 transistor, so that the clock load, okay, the clock load is reduced to half, okay. But here you can see all the node voltage in the latch will not experience the full voltage swing, okay. What is full voltage swing means either 1 or 0. But here you can see there is a few node voltage which will lack this full voltage state. So here if you see whenever the input values, so this is nothing but a negative latch. So I'm considering the input value is VDD. So if the input value is VDD means this transistor will conduct. Okay, if this transistor will conduct means this voltage goes to 0. Okay, and you can see this negative latch. Okay, so this is nothing but a negative latch. Okay. So this is 0. So if this is 0 means you know that the PMOS pass transistor is strong 1 and weak 0. Okay, since the input of this one is 0, so it will the A will go to minus VTP. Okay, so I can return it as VTP. So you can see instead of going to 0, it will goes to minus VTT. Okay, so it will lack a full voltage swing. So it is 0 only, but it cannot able to drive the output again.
This is wrong.
So you can see here, so it is also called a split output. This is nothing but a positive latch, okay. So when now the clock is 1 and the input value is 0. So if the input value is 0, this transistor will conduct. So VDD will goes to here, okay, and the output value is, so this will be 1, right? So this will be 1 and the clock value is 1. So since NMOS transistor, NMOS pass transistor is weak 1 and strong 0, okay. So you can see if this is conducting and I am giving a 1, so this A will goes to VDD minus VTN. So instead of 1, it goes to VDD minus VTN.
Right.
But the output is going to 0, okay. So this will limit the amount of VDD scaling possible on the latches. So this is one disadvantage, okay. So next we are going to show the design of the specialized single phase edge trigger register, okay. So whenever the clock is 0, so if clock value is 0, this transistor will conduct, each transistor will conduct M2, M6 and is conducting, okay, is conducting. So if the input value is 1, so if the input value is 1, M1 is also conducting, make my X to 0, okay. If this is conducting, this will discharge the value of X, okay, and since this is 0, the Y value goes to 1, okay. If Y value is 1 means M7 will conduct, but M8 is off, okay. So the output Q bar is floating, right? So whenever I can give the clock value 0, the output is going to float. So this is my first condition, okay, when the input is 1. So what happens when my input is 0? If the input is 0, okay, M3 will conduct, M3 and M2 is conducting. So the X value goes to 1, okay. Since the X value is 1, M5 is on. M5 is on, but M4 is off. Okay, M4 is off, but Y value is 1. If Y value is 1, okay, so again the Q is floated. Q bar is floated. That is in the hold mode. Okay. But you can see the input value is inverted and it is in the X. Okay. So next I'm going to give clock is equal to 1. If clock is equal to 1. So if clock is equal to 1, M4 and M8 will conduct, right? M4 and M8 is on. And you can see I'm going to give my input as, for first condition, input as 1. So if the input is 1 means M1 is conducting, M1 is on. So the X value goes to 0. So if M1 is on means X value goes to 0. Okay. And you can see whenever my input is 1 means the X value is remains in 1. Okay, here initially the Y value is 1. Okay, so this one will make my M7 transistor and the M8 to turn on. Okay, so the M7 and M8 to turn on. So since the Y value is 1. Okay. Previously, if you see the input value is 1 means Y becomes 1. Okay, so if Y is 1 means M7 and M8 will turn on. Therefore, my Q bar is equal to 0. Okay, and the Q must be 1. That is equal to my input. Okay, so it will work as a positive register. Okay, so what happens when input is 0? If input is 0, M3 and M3 is on. Okay, M3 is on, and if D value is 0. So what about clock 1? Clock 1 is open circuited. So what is my previous X value when ln is equal to 0? X is equal to 1. Okay, so X is 1. So since X is 1, and you can see M5 and M4 is on. So this will make my Y to go to 0. If Y go to 0 means M9 will turn on. Okay, M9 will turn on. So my Q bar value becomes 1. So Q is equal to 0. That is nothing but your input. Okay. So if you see the setup time, okay. So what is setup time? Setup time for so the setup time here, it represents time for the node X to be valid. So so the input has to reach the X. So it is nothing but 1 inverter delay. Okay. So next hold time, THT. So that is also equal to, that is this hold time must be less than this inverter delay. Okay. And since the data is holding here, so from here to my output, okay, so that represents the propagation delay, right? So TPD. So the input from the X to reach the output Q, it has to cross 3 inverters. So this is 1 inverter, second and third. So TPD, propagation delay, is equal to the delay of 3 inverters.